to yeah, read the description. I have let's see. So I'm generating something. Some number. A number of numbers even. That have a big chance to interfere. As in they are a sum of the same factors. So if one of the numbers is say 100 and another one is 1,000, then another one can be 1,000 plus 100 or 1,000 minus 100. So adding and subtracting these numbers will then interfere and result in also very small numbers, for example, after subtracting two large numbers. We sort these by absolute value. So the in absolute value, smallest numbers are up front in the values vector. And the comment here is we assume a cubic polynomial where well, this is just a typical way that depends on its roots. And then, yeah, the roots are indistinguishable. If you swap any two roots, then this formula doesn't change. So we also demand that this holds. Well, actually, this and then this. So. Oh, there it is. We should repeat it here. Shut up. Okay, so let's see, we have here yep, so if only R0 is real, then the other two are complex and they must be complex conjugates, which means that their absolute value is equal. And R0 is less though, then we have automatically this equation, while if R2 is real, then the other two must be equal. And so then it must look like this. These two are equal and then R2 is larger. Then of course, theoretically, we still have a possibility that R1 is the only one that is real. But the absolute value for R0 and R2 must be equal, therefore then everything must be equal. But I don't want to deal with D, so in that case we just swap R1 and R2, so that we still get the KC in this case. You could also swap R1 and R0 and then you would get that one. But yeah, absolute value, all three equal. No. It's gonna happen anyway. So nevertheless, by this rule, if R1 is complex, then that means that R0 is complex, not R2. Okay, that was nonsense. You can have this is complex or that is complex. That's the other way around. if R1 is real, then all of them are real. And if R1 is complex, then either R0 or R2 are complex. So we can now generate every possibility. Case A, all three are real. So it is 1 over all the indexes of all values. And construct R2 from that. It's just a double then. But okay, I store everything in the complex anyway. So these are real, right? I mean, let's add a comment. So, okay, it's case A. All three roots are reals, even though it's stored in a complex. Standard complex. Okay, and since these things were sorted by absolute value, if the index of R1 is less than or equal the index of R2, then the absolute value will be less or equal. So by stopping on this condition here, we assure that this is the case. And then we do that again for the index of R0. So this is also the case. And then we have generated all possible cubics with real roots. Extra assert here, but it has never filled me yet. And then I call a function that takes those three roots. And then we have the B, case B. I just split that up in the real part and the imaginary part of the complex roots. So here I say R0 and R1 are complex. Let's write them out as the complex number. Let's call I real, let's call real here simply alpha. And beta for the imaginary. Oh, here I have the same. I'm just gonna copy this from the YouTube description that I wrote. No, where is it? Definitely use an alpha. Yeah, there it is. So the one with the plus here, that is the plus. What? Oh, wait a minute. It's gonna depends on we start with a negative number or a positive number. Doesn't really matter, of course, but still. Let's try to run over all positive numbers here in beta. So then this is the plus, the R2 is the plus. You're gonna be kidding me. R1 and R2? Huh? This means that case B. Maybe R0 is real. Oh, okay, it's the other way around. Yep, there's one. R1 and R2 are complex, and I'm using. What this one is real. R1 is then the one with the minus sign. R2. So in case C, then R2 is real. And the minus sign is R1. So the R0 is... No, still R1 then. Whatever. Root, good. That rhymes. Okay. Thought there was something I was forgetting. What was it? Oh yeah, I do want to check actually if this is if the betas are positive. Not sure at all. Let's just print them out. Wahaha. The lazy programmer. Just print it out. Values I beta. That's both positive and negative. Okay, that's shocking. It starts off with the negative numbers. Oh, they're just not an odd number. Okay, yeah. I think at the very least they are different in absolute value, all of them. You can at least check that, I guess. Let me just start at one or something. And assert that the absolute value of this thing is unequal the absolute value of the previous one. There's a better way. Just the previous one must be lessive, not just unequal. Yep. It really shouldn't matter, but yeah, I wrote here that this one is the -1, so let's just make beta positive. Because by not doing this, we would have a kind of a random. It really doesn't matter, but. Do this anyway, like this. Maybe it's more clear if I split it up though. Say I'll make an alpha. And a beta. Go to swap these as well. The -1. This now must become alpha minus beta. I just invented a new Greek letter, the geta. It went completely unnoticed. Well, not entirely, I noticed it. Okay, yep. Right. So in this case, we run from the largest absolute value to the smaller ones, because R2 must be larger in absolute value. And then that means that as soon as we reach a value that is no longer larger, why is this not less than or equal? Equal is allowed, yeah. So as soon as it is no longer larger or equal, aka less than, then we stop, because all the next ones will be even smaller. And now, of course, we do the same thing here, but then the other way around, because R0 must be less than or equal. So as soon as it is larger, then stop. This generates all possible cubics with roots from this palette of values stored in values. I can add this one also, but then it becomes much slower. Even this is already slow, unfortunately. Okay, so now we are here, and now we can calculate the coefficients, C2 and C1 and C0. And the standard rule here is, yeah, just to make it a double, and you can't otherwise convert it. The imaginary part of of each of these things should automatically be 0, because, well, here we have either R0 and R1 are complex, and then complex conjugates, so the imaginary part cancels out, or R1 and R2 are complex, if any complex are there at all, and then they still cancel out. And the same thing happens here. If R0 and R1 are complex, then we get R0 plus R1 times R2, and so the conjugated imaginary part cancels out here, while of course a plus b times a minus b is just a squared plus b squared, so also here there is no complex part left. And finally the same thing here, either this or that as a multiplication between two complex conjugates. Complex values, so everything is just real. The imaginary part is it's really 0. Okay, now currently I'm just calculating the square root of C0 squared minus the cube of C1, which is very promising. And then I say, okay, so if this value is much smaller than 1, then I expect the absolute value of R0 to be much smaller than the absolute value of R2. And if this is significantly not the case, namely it's even larger than 100, well, yeah, in all reasonableness, you would like to see also 1000 here. Then I print this out, and something went wrong in the detection. And the other way around, if the absolute value of R0 is significantly less than the absolute value of R2, which is what you want to detect, then this better be also smaller than, well, 100. I even made it 1/10, so you can already see where it's going to fail. But if say 1000 here, then we use 100 here. And then if it is larger than 100, then something went wrong. No, it did get it wrong in this case, so I even made it a 10th and it still went wrong. Oops, we can investigate when that exactly happens. So for example here. The reason that it happens is because the absolute value of R0 is much smaller than the absolute value of R2, but not much smaller than the absolute value of R1. In fact, they are each other's opposite here. And the problem is that b becomes, well, small, 1. So b to the power 3 is very small compared to the c squared. So you get c squared divided by 1 and then the square root of that again, so you just get the value of c here. So that is definitely not less than 0.01 and not even less than 0.1, it's just huge. Complete failure. Which means that we would not detect this. We will only detect the cubics where the absolute value of R0 is much less than both other roots, both R1 and R2. Let me look at my description again. I had an idea. I wanted to plot Yes, I can plot the ratio. Let's say we just look at the ratio between the absolute value of R0 and R1. And I can plot that against any of the possible formulas. Yeah, we just begin with this one. And then maybe make a double log plot. So then I'm no longer using boundaries at all. You just take the log of it and then plot it. So this is just, testing some boundary, and then if things look really wrong, we print it. But you can also use every data point and simply plot it. So I want to plot now is a point, let's say horizontally, we put the detection, so F. So I'm gonna take the log, take the log 10 of F. Call it X. I'm going to plot that horizontally. And then vertically we plot the log of the ratio between absolute value of R0 divided by the standard absolute value of R1. That should be detectable. It should probably give a nice plot. Okay, so we have there must be some points. I'm going to do add point, x, y. Add point being a part of quick graph. So I'm going to need a graph. Quick graph. Let's see. Let's call that just graph. Let's pass this front here. No, let's pass it at the end. Quick graph is add point const. Probably not. Hello, Amon. Did you read the description below the video that explains what I'm doing? That is non-const. That just passes the thing by reference. Graph. And I want a certain point style. That was, yeah, and I forgot it again, of course. Is that not Cairo window? I think it's a draw point style. Yeah, maybe all the styles are in namespace draw. Yeah, this isn't draw. Okay, it's draw point style. And we must set field shape to the 15, I think. Just a single dot. Field shape is 15. How does this work again? So we have a draw. point style. Then you can call something on it. I think this works. And yeah, I don't know. Maybe it makes more sense to just create the thing once. Style. Can you create it like this or not? I doubt it actually. No, you have to add braces as well. Braces. Parentheses. So. Okay, we need a quick graph, which the namespace is quick graph. Let's carry a window. Need a header for that. Oh no, I need to add it to CMake, I think, because I'm using the Cairo window. Yep, otherwise I won't link at the very least. Oh, this drags in everything. Okay. Include. That was a standalone file so far, but now it's going to require my whole palette of utilities and everything. So whenever we call roots now, we have to pass the graph object. Which we will create here, I guess. I think that thing needs a title. The title is going to be no, I don't know, small root. And then horizontally we have the square root of C is the constant, must be C3. C3 squared divided by C2 cubed. The absolute value of that. Or the norm. It could be complex, I think. No, it's not complex, just the absolute value. These are the cubic coefficients, so they are real. And then vertically we have oh, it's even the log 10 of that. Okay, the log 10 of the absolute value of R0 divided by R1 at the moment. So the log 10 of the absolute value of R0 divided by the absolute value of R1. And I need the log 10 of that whole thing. Yeah, this is just a half times log 10 of this. But whatever. Title X level, okay, X range and Y range. Can I just leave that out? The Y range is determined. I have to specify an X range. Makes sense. Range. The range, the X range, so that would be the range of this square root thing. And then the log of that. Okay. Let's try -4 till 3. Not sure if that is enough or too much, but we'll see. And oh, wait a minute. The automatic determination of the y-axis only works if I add a function, which you don't have. I'm going to have to add a y range as well. So let's just use the same for now. And I think I have to add a function anyway. That's kind of silly. But I believe that is necessary. So the add function on the quick graph is requiring just a function. Horizontal line at the y equals 0. Maybe draw a diagonal line. Okay, yeah. I did this before. Add function. Let's do this one. That's not diagonal, of course. Steal that color. It's almost not visible then. Let's make it a diagonal line anyway. Yeah. I'll probably... Yeah, nothing works. Okay, let's give this thing a name. All of this is necessary. Well, not that. And all of this. No mention member function for call to add points or not. Maybe we should do using namespace. Oh, we should pass it as a point, not as two separate coordinates. Where is my small root? Yeah. Nothing. I'm not seeing any dots being added. No. Nobody knows what's wrong. Got to initialize. Well, that should be visible. To -1 is being added a lot, which is totally in the range -4 till 3. Yet we are not seeing it. Why not? Let's make this thing considerably faster. Removing that as well. How can it still be slow? Yep, really not drawing anything. We're waiting for space or something. No space. Enter, no Q. What the hell? Nothing. Why? It's also using 100% CPU, which is annoying. In a minute, I already know that it is in this range, so let's not print this. Might make it a little bit faster. This is 200. I think it runs till 7 to the power 2 now? No, 7 to the power 3 then. 343, so that would be the last one. B is not being printed at all. No. It's already waiting in. Wait for key press. Oh, that's because this is a 1. Yeah. Okay, also that doesn't really matter then, because so the 0 is A, 1 is B, 2 is C, and then 3 we don't get. Because it's just not drawing anything. I'm also not seem not to be able to terminate it with a quit. It did detect my cue, but then it still is hanging. Why? Oh, it's erasing everything. So it's not drawing anything, but it is erasing everything. Destruction of the points takes a long time, apparently. Well, that's interesting. Remove if, erase points. I can't find it. Well, plot lines, okay. So plot points, there it is. Ah, that's what I was looking for. So we have 27 million invisible points. And they are not visible because all of them are not a number. Well, this one is a number. This one is not a number though. So the next one. Everything stops drawing as soon as you try to add something that with a not a number. It's always a possibility. Let's not add points that are unplottable. And I'm also not feeling very certain now about this 15, so let's just make it a 1 for now. Now I really want to see something being drawn. Oh yeah, absolutely. So here, bang. Now let's go back to the 15 then. I could just 27 million points. Nice. Oh yeah, that makes sense. It's never higher than 0 because R0 is less than R1 per definition. In other words, this is always less than 1, or the log is always less than 0. That didn't make any sense to go all the way up till 3. Feels slow. Oh, that's B. B0. Should use different colors, I think, for B. Because I'm kind of interested how that looks. Well, I think the general picture is clear. It saturates against 0, of course. And now you have a nice curve here. And then we also have a curve here, it seems. And then the rest is filled in more or less. And there's some blocky stuff going on. Which is in the end irrelevant anyway. So let's see if we can speed this up and still get the same picture. Let's start with trying just to not a very significant speed up yet. Also, let's pass the point style to the roots. So this is point style case C. Point style case B. Color, I have to work with index. Keep hating that. Yeah, we are clearly already missing a lot, right? You can still see this curve, and you still guess that this is filled up really, but it got very sparse. I'm afraid I'm going to do something very slow. Even adding that one back. I want to see how it looks then. And while it's running, maybe you can do some thinking. So let's say I'm interested in detecting when R0 is, well, 1%. The absolute value for R0 is I mean, when they are more or less equal, it does not warrant or needs a separate algorithm. But if the absolute value for R0 is much less than the absolute value for R1, maybe even the thousands, but okay. You could argue, well, from 100. So that means we want to detect all the cases where we are below the -2 here. In that case, it would be 1/100th of R1. And well, that strongly correlates with -2 on this axis, although that goes all the way up till the -1 here. But you might detect this one. This dot is less than the -2 here, but yeah, not below the -2 there. Well, on the other hand, if you say, well, I only want to get this one, so we must be below this value, then you would miss stuff, let's say, so go a little bit to the right, so we don't count it anymore, and then as low as possible, so here, so this dot would be missed then, because it's not part of that part, this dot. But okay, then it is not even 1,000, and I said maybe it only gets interesting when it's 1,000th or worse or smaller. Yeah, let's say we want to certainly detect it if it is less than -3. We don't want to detect it when it is above -2. So if we don't want to detect it when it is above -2, that means that this line here, this vertical line, is the border. So we would detect these. Actually, all of this, yeah. Oh, well, no. Works for me. The looks of it are, these points are on the line x equals y. Not sure if you can see it, but it's a very faint diagonal line here. You can also see it here. It seems that further down you go here, and that it will probably exist, there's always then a line going up, maybe twice the slope or something like that, or the same slope more or less. This is also now a straight line. Which would mean that we could fill up this hill area, everything. Which means that if we don't want to detect, well, if that is the case anyway, then Is it the case? That is the question, of course. If this all, the further the vertical line that I was drawing is going through this point here. So if there is points on this side, then that line has to shift. But I never ever want to shift it further than the -3 here. So it would be interesting to understand if it is possible to have a point here or not, or a little bit even to the left of that. This is definitely too slow. I want to reproduce the boundaries of this area. This boundary is very clear. This boundary must be detectable somehow. If we could just find the boundaries, then we could draw all the possible combinations of powers of the coefficients in one picture, which then would give a way better, a more precise way to single out everything that is below a certain horizontal line. How do we find the relationship between the coefficients on this line, for example? Yeah, let's talk to ChatGPT. I mean, I know it doesn't understand this, it doesn't understand anything, but it still helps me to think a little bit. This picture's not changing anymore, so I'll put it here. Only 25 responses left. Oh, tomorrow. We already passed that, I think. No, we didn't. So I have 25 responses left for the next hour. It's good enough. Do you want to start over? Maybe not. Restate the problem. Got it. So let's R0, R1 and R2 be the three roots of the monocubic P is that. But I don't want to talk about this anymore. I want to call this C2. That's way easier. That's just the index of C corresponds to the exponent of the X. What else do you want? So this must be 1. And then that is the 0. That lots of generality, let this be true. The corresponding equation is then this. In other words, and then we can repeat that. The plus was this one, so that is C2. That's this one. Good. Now I plot the log 10 of square root of the absolute value of why is it called C3? Seriously. What am I plotting then? Damn it. We're plotting X is the log of F, which is C0 divided by C1. Huh? C0 being the multiplication between the 3. That is C0, yeah. So it is C0 squared. divided by C1 cubed. Let's fix my program as well. C0 divided by C1. What was I thinking? Yep. Yeah. So for a given ratio of well, C naught cubed divided by C1, sorry, squared divided by C1 cubed. That is for a given point on the x-axis here. This never gets below a certain point. So this is the lowest point here, and this is the lowest point here. Not there, but here, the lowest point. So that describes this curve. I want to know that curve. So there is a limit to how small R0 divided by R1 can be. What is the relationship between no, we can just combine it like this, between and this minimum value of I see you have to do this numerically. Copy. If it doesn't know the answer, then the answer is you should use a numerical approach. It's tiresome, of course. Can you just do that? I don't see it. So no, maybe not. Yeah, I mean, it goes on with let k be that without removing the absolute value of R1 again. Oh, it does. Yeah. Less than or equal 1. Case. No. I mean, that would be just a diagonal line here. Well, not even. A half here. This is square root there. It's just not true. Well, so far my graph is just, which is still just generating real values, real roots. So R0 and R1 and R2 are all real. And I might as well concentrate on this function here under those circumstances. No, I never tried that unpronounceable name. Nor should you. Oh shit. Are we still alive? Yes, I did run out of memory. Too many points. I think should be okay again. Yep. Yeah, so the absolute value of A divided by B is the absolute value of A divided by the absolute value of B. At least if everything is reals. I'm not sure if that also holds for complex numbers. Tell reals anyway. And of course, the minus can be removed because of the square anyway, and then the square can be distributed. And then we can apply the absolute value again on each vector separately. And even inside the square root. So this definitely holds here. And then I still have to divide that by the absolute value of the cube of that, which is can also be written as the absolute value of the whole thing cubed. But I can't turn that into separate. Can't get the absolute values around the R zeros here. I mean, around the roots themselves. It just remains like this. Maybe we should first take the cube and then take the absolute value. I have the feeling that let me see. The sum of, if I make this sum as large as possible, so not something I gain something with then. Yeah, because you could see in the graph that if you make this smaller, then you can make that smaller. So I'm going to argue that making it small as possible for a given set of absolute values of rows. We'll make the minimum possible value of k smaller, because let's verify this. So right now I'm picking roots. We're talking about A here. We're picking roots from the table of values ordered by absolute value, but that quickly iterates of varies then between in sign. So you have some root and a negative of that root. And I'm saying that we reach the lower part of the graph if all roots are positive. So I don't want to store negative values anymore. So we do if val is larger or equals 0, then we push back the value. Otherwise, I don't want to take it into account anymore. And that should reproduce the lower part of the graph. That's my idea now. Doesn't. It doesn't. Shocking. Man, why not? Okay, I have a good idea. I need to exercise a little more than except just sitting behind my PC. So I'm finally going for a walk again, since weeks, it seems. Because I just have to, really. It's just stupid, man. I should do that every day. And then after half an hour walk, I will arrive in a cafe, and there I will drink a cup of tea while doing mathematics. So I'll just bring a pen and paper. It is raining though. Yeah, I can put on a raincoat. Or bring an umbrella. I have a, yeah, do that. Because clearly I need to scribble down a lot of formulas here before I can say something sensible about it. Kind of shocked that this did not work. What is wrong with my reasoning then? This reasoning. I mean, if you have a certain cubic with 3 real roots, so you have a given ratio of absolute value of R0 divided by the absolute value of R1, then you might as well toggle the sign of R0 and or R1 without changing K, which is our vertical axis in the graph. But that does have influence on the horizontal axis, namely, you can write it like this. This part, the numerator does not change. The denominator, however, can be made smaller by picking the same sign for each. Yep. So we make all of them positive. That means that the k does not change, so vertically nothing changes, but this value becomes smaller. So we move in the graph, we move, well, should draw it again. Should draw it again with without doing this. So if you are, say, you're here and you have negative roots in it, then you can just toggle the sign of the roots till they are all equal. And what will happen is that this won't change, but this will get smaller. And then with all the same signs, you'll end up there for those roots. Making it possible, well, making it not part of the graph anymore. Because I want to find this function, right? Bottom. Yeah. No. Wait. Is that true? Oh, yeah. So it's the other way around. You want to go as far to the... Yeah, okay. Yeah. So by making them the same sign, we move horizontally to the left. But in order to find this curve, we want to horizontally move to the right, actually. Yeah. Okay. No, well, at least I get that one now. Then. That doesn't make things simpler, however. So we must make this as small as possible. So for any given k and s, we should choose the signs of all roots such that is as small as possible. No, sorry. Is yeah, small as possible, and therefore is as large as possible. And this is nonsense. So for given absolute values of the roots, we want to pick the sign such that this sum is as small as possible. Because then we end up at the curve that you look for. Yeah, that's not exactly true, of course, because we also have that in the enumerator. But yeah, this goes with the square, and then this is going to grow with the cube. Okay, so I should add a cube probably. We'll grow with the cube of R2. While the numerator grows with the square of R2. And making smaller again. Okay, I'm just going to do this on it and then leave. I'd like to print this page. Can I print it? Print. Just this one page. Which page is this? Page 7. Okay, I'll be back later.